Hi, my name is Pamela Franco.
And my name is Andrew Paraso, and we are both graduate students at the University of Rhode Island.
This poster discusses determining layer thickness and understanding moisture-related damage of state-owned roads using GPR and capturing such in a GIS-based inventory. Starting with the abstract, the Rhode Island Department of Transportation, RIDOT, has a significant inventory of state-owned roads of which layer thickness and moisture-related damage is uncertain. The assessment of roads via coring and visual inspection can be costly and time-consuming, while the use of GPR can be faster and non-destructive. Through collaboration between the University of Rhode Island, Roger Williams University, and RIDOT researchers, the efficiency of using GPR at traffic speeds to determine asphalt thickness and moisture-related damage of rural state-owned roads was evaluated. The ultimate goal of this effort is to establish a system for collecting and viewing pavement layer thickness and moisture-related damage on a network level for RIDOT to use the information to better plan, prioritize, and properly allocate funding for pavement-related projects.
Data for this project was collected using ground-penetrating radar. One of our sites was Route 117, located in West Warwick. Approximately 1.3 miles of GPR data was collected for this site between Route 95 to the east and Route 2 to the west. Data was collected in both the eastbound and westbound directions in the center of each lane. The Rhode Island Department of Transportation wanted to know thickness and damage estimates for reconstruction planning purposes. Due to the age of the road, Rhode Island Department of Transportation also wanted to know if any composite sections existed. For data collection, three 2 gigahertz antennas were mounted on the front of the survey van. The antennas were then connected to GSSI's SIR-30 located inside the van. Antennas positioned in both wheel paths and in the center of the lane. Data was then collected at a rate of 1 scan per foot. For the data analysis of Route 117, Figure 4 shows a B scan of a portion of the road. The top reflection shows the surface of the road. The red points were manually selected using a GPR analysis software called Radan. The red points indicate the bottom of the asphalt layer. The asphalt in this portion of Route 117 was underlain by macadam. Asphalt thickness, dielectric constant, and GPS coordinates of each location were then exported into an Excel file. Cores were then taken to verify the thickness determined by the Radan file. Core number 5's location is labeled on Figure 4. The estimated asphalt thickness was 4.5 inches, and the measured thickness was 4.6 inches. Excellent correlation between core thickness and estimated Radan thickness was achieved, shown in Figure 6. Interactive Google Maps were used to display core locations, asphalt depth, and composite locations along the roadway. The core locations aided in verifying asphalt thickness locations. The asphalt thickness map showed ranges of depth for asphalt. Each color indicates a specific range. The road had been reconstructed many times, and therefore asphalt depths can differ. Based on Radan scans and cores, composite sections were also discovered. Composite sections of Route 117 were labeled in the interactive Google map. Radan was able to locate the start and end portions of the composite sections, aiding the Rhode Island Department of Transportation in reconstructive planning.
Now for the dielectric of Route 117. Shown here in Figure 8 is a graph of the surface and subsurface dielectrics going eastbound on Route 117, with normalized dielectric on the y-axis and distance on the x-axis. The dielectrics were normalized to the average road dielectric of 7.9, shown in the top right corner. The surface dielectrics are shown in blue, and the subsurface dielectrics are shown in orange. The red lines are the top and bottom limits of dielectrics that are within plus or minus 15% from the average normalized dielectric. Areas that contain values outside of these limits are expected to have more damage that could be contributed to moisture than areas within the limits. The graph shows that the surface and subsurface dielectrics follow the same correlation and are approximately the same values. Also, it can be noted that the first portion of the road going eastbound is old pavement and then transition into new pavement at about 40,250 feet. This is indicated by the portion of the graph before 40,250 feet being much more variable than the latter, more consistent portion of the graph. Overall, the use of GPR was successful in determining pavement thickness and dielectric constant of rural state-owned roads, which aided in the assessment of the condition of the road. The University of Rhode Island, Roger Williams University, and the Rhode Island Department of Transportation worked in conjunction to identify candidate roads and collect data for this project. The data was collected using a SIR 30 survey system and was post-processed to determine pavement thickness and dielectric constant using GSSI's software system, Radon. The accuracy of using GPR to determine pavement thickness was investigated by comparing estimated pavement thickness values from GPR with cores that were collected from the road, as summarized in Figure 6. Google Maps was used to create user-friendly interactive maps that display the pavement depth and dielectric values along the roads. This information can also be converted into RIDOT's GIS-based inventory to aid in the process of planning for reconstruction or rehabilitation. The objective of this project was to use GPR as a non-destructive process for collecting and interpreting pavement thickness and moisture-related damage. The information obtained will allow RIDOT to optimize their system of planning for future pavement-related projects. And for acknowledgments, funding for this research was provided by the Transportation Infrastructure Durability Center at the University of Maine and the Rhode Island Department of Transportation. Thank you.